What if it was wrong? Imagine if the very fabric of our universe, the vast distances, the flow of time, isn't fundamental at all. What if it's more like an illusion, woven from these bizarre, invisible threads of quantum entanglement?
That's a pretty mind-bending starting point.
It really is. And that's the idea we're diving into today, this huge quest in physics to somehow unite Einstein's gravity with the super weird world of quantum particles.
Exactly. Our mission today, if you will, is to unpack this really radical idea, the emergent spacetime hypothesis. We'll need to start with the basics, general relativity, quantum mechanics, get grounded there first.
Right.
Then we can trace how the theory is developed, trying to bridge this huge gap between them. We'll get into some pretty grand conjectures.
Oh, I bet.
And then look at the challenges, because there are big ones, and what it all might mean for reality itself.
And the core conflict is just fascinating, isn't it? You have these two theories, both incredibly successful.
Monumentally successful.
Right. But they just fundamentally don't agree on how the universe works at its deepest level. So how could they possibly be bridged? What are the clues?
That's the multi-billion-dollar question, isn't it?
Yeah, probably more. So, okay, to really get our heads around this emergent idea, we need to properly understand these two pillars first, the ones that refuse to cooperate. Let's start with Einstein's picture, general relativity.
Okay. GR.
This came out of his special relativity in 1905, fully formed around 1915. And it just completely flipped our view of the universe, right? Space and time, he said, aren't separate things. They're woven together.
Into space-time, a four-dimensional fabric.
Exactly, a dynamic entity. And here's the kicker. It's not just a static background. Matter and energy actually warp it, curve it.
Right.
So gravity, what we feel as gravity, isn't really a force in the traditional sense. It's just us, objects, everything, following the straightest possible paths, geodesics, through this curved landscape.
The classic summary is, matter tells space-time how to curve.
And curved space-time tells matter how to move.
Yeah. And the key things to remember here are, it's smooth, it's continuous, everything happens at a specific point, and crucially, cause and effect are strict. Nothing travels faster than light.
The cosmic speed limit, it's all very geometric, deterministic, and local. But then
Does the other guy.
quantum mechanics.
Right, the other cornerstone. And it describes a world that's, fundamentally different, almost paradoxically so, where GR is smooth and predictable, QM is jumpy, probabilistic, discrete, and the really tricky part, non-local.
Non-local, that's the entanglement bit, right?
Yeah.
Einstein's spooky action at a distance.
That's the one. At its heart lies quantum entanglement. Imagine you have a process that creates two particles, say photons, linked in a special way. Before you measure them, properties like their spin are in a kind of limbo, a superposition.
Both up and down at the same time. Sort of.
Sort of, yeah. It's a mix of possibilities. But the spooky part happens when you measure one. Let's say you measure the first photon and find its spin is up. Instantly, and I mean instantly, its entangled partner spin is down.
Regardless of how far away it is. Even light years.
Regardless of distance, Earth to Andromeda doesn't matter. The connection is immediate. It's like, imagine two coins magically linked. You flip one here, it lands heads. You instantly know the other coin, wherever it is, must be tails, even before anyone looks at it. That's the spookiness.
Okay, yeah, that does sound spooky. How do we know it's not just fiddlemen? Yeah, they secretly agreed beforehand, like, okay, if you're heads, I'll be tails.
That's exactly what physicists wondered for decades, this idea of local hidden variables, some hidden instruction set they carried with them. But theorists like John Stuart Bell in the 60s figured out how to test this.
Bell's theorem.
Precisely. And experiments, particularly by people like John Clauser and others since, have basically slammed the door on that. They've shown pretty definitively that there are no local hidden instructions. Entanglement is genuinely non-local. It's an informational link that just doesn't care about space.
But hang on, does that mean information travels faster than light? Doesn't that break relativity?
Good question. Crucially, no, it doesn't allow faster-than-light communication, because the outcome of the first measurement you make is totally random. You can't control whether you get spin up or spin down.
Right.
You only know the correlation after the fact once you compare results using normal light-speed communications, so causality is safe. Just barely.
Okay, barely. So let's sum this up. GR says everything is smooth, local, geometric, spacetime's the stage. But QM, with entanglement, says there are these instant, non-local connections that ignore the stage completely. Am I getting the clash right? Is it really that stark?
You're getting it perfectly. It is that stark. It's a conceptual chasm. GR spacetime is king, smooth, continuous, local interactions rule. QM, you have these non-local links, these informational correlations, that seem utterly indifferent to the geometry GR holds sacred, that Earth to Andromeda link you mentioned. For entanglement, the distance might as well be zero.
Wow. Okay. So that really forces the question, doesn't it? Which one is more fundamental? Is space-time the real bedrock, and entanglement is just some weird quantum quirk happening within it?
Or
Or is the entanglement network, this web of quantum information, somehow more fundamental?
yeah.
And space-time itself, the geometry, the distances, is that just something that emerges from the entanglement?
Exactly. And that second option, that's the emergent spacetime hypothesis. It's a monumental shift. It suggests geometry isn't the stage. It's more like a shadow play projected by deeper quantum rules.
Okay, so how did this idea move from just, like, philosophical musing to actual physics? Where did the concrete evidence start coming from?
Well, the first real hints came from a very unexpected place: black holes. Back in the early 1970s, Jacob Bekenstein and later Stephen Hawking made this absolutely stunning discovery. They found that black holes have entropy.
Entropy, like disorder,
Yeah.
or information content.
Information content,
Yeah.
essentially, a measure of the hidden internal states. But the really shocking part wasn't just that they had entropy, it was how it scaled. For normal things, entropy scales with volume, more room for stuff, more entropy.
Makes sense.
But for black holes, the entropy was proportional to the surface area of the event horizon, the boundary, not the volume inside.
Whoa. So all the information about what fell in is somehow stuck on the surface.
That was the mind-blowing implication. Like all the books in a library being stored not on shelves inside, but somehow encoded on the building's outer walls. This area law was a huge clue. It led Gerard Hooft and Leonard Susskind to formulate the holographic principle.
Holographics,
Yeah.
like a hologram.
Exactly like a hologram. The idea is that all the information needed to describe a 3D volume of space can be fully encoded on its 2D boundary, just like a 2D holographic plate stores a 3D image.
So, our 3D universe could be a projection from some lower dimensional boundary.
That's the radical suggestion, that maybe information is more fundamental than space itself. Space is just how that information manifests.
Okay, the holographic principle is already making my head spin. But it was still kind of a principle, right? Not a precise mathematical model.
Correct. It was a powerful idea, but lacked a concrete mathematical framework. That changed dramatically in 1997 with Juan Maldaceno's breakthrough, something called the AD-SCFT correspondence.
AD-SCFT. Sounds complicated.
The name is a mouthful, definitely. But think of it like this. It's a precise mathematical dictionary, a duality and equivalence between two seemingly very different theories.
Okay, a dictionary between what?
On one side, you have a theory of quantum gravity, often string theory, living in a specific kind of curved spacetime called anti-de Sitter space, or ADS. That's the higher dimensional bulk.
Right, the inside of the hologram, maybe?
Sort of, yeah. And on the other side of the dictionary, you have a quantum field theory, crucially, one without gravity living on the lower dimensional boundary of that 8S space. That's the conformal field theory, or CFT.
So gravity in the bulk is somehow equivalent to quantum stuff without gravity on the boundary? How does that help?
It helps immensely because it's often a strong, weak duality. When the quantum physics on the boundary is strongly interacting, really complex and hard to calculate.
Like quarks inside a proton.
Exactly. Like the quark gluon plasma they create in particle colliders, or maybe even some high-temperature superconductors. When that boundary theory is hard, the gravity theory in the bulk turns out to be weakly curved, relatively simple, and easier to calculate using Einstein's equations.
Ah, so it's a computational tool. You can solve hard quantum problems by translating them into easier gravity problems using this dictionary.
Precisely. It's been incredibly powerful for exactly those kinds of calculations. For example, one specific version relates type IIB string theory in 5D ADS space to a 4D quantum theory called Enning-4 super-Yang-Mills.
Okay, so the dictionary connects these two different worlds. What kind of entries are in this dictionary? What translates to what?
Well, there are lots of entries. For instance, fluctuations in the gravitational field in the bulk correspond to something called the stress energy tensor in the boundary theory, basically, how energy and momentum are distributed.
Okay.
A black hole sitting in the bulk spacetime corresponds to a hot thermal state in the boundary quantum theory, like a boiling soup of particles.
Interesting.
But the entry that really blew things open for emergent spacetime connects back to what we were saying about black hole entropy and area. It turns out the area of a specific kind of minimal surface in the gravitational bulk
A geometric quantity.
is directly proportional to the entanglement entropy of a region in the boundary quantum theory.
Entanglement entropy, so a measure of how much entanglement there is.
Exactly, a purely quantum informational quantity. This direct link between geometry and entanglement was monumental.
So geometry is entanglement in this picture, or at least directly reflects it.
That's the profound insight. This specific relationship was quantified in 2006 by Shinsei Ryu and Tadashi Takayanagi. Their formula, the RT formula, gives a precise equation. Entanglement entropy equals the area of this special surface, divided by a constant. SA equals area for GM.
Wow. Okay, so it's not just a vague idea, it's a calculation you can actually do.
Yes. It provides a quantitative handle. It strongly suggests that, as some physicists like to say, spacetime is built from qubits from quantum information. The geometry you see in the bulk literally maps out the entanglement structure on the boundary.
This sounds like it could explain the holographic principle more deeply.
It does. It shows how an entire dimension of space, the radial dimension going into the bulk, can literally emerge from the entanglement patterns in a lower dimensional quantum system living on the boundary. Mark van Ramsdonk had a fantastic thought experiment showing this.
Oh yeah, what was it?
He imagined two separate regions on the boundary CFT. If they are highly entangled, the RT formula says there's a minimal surface connecting them with a small area, which corresponds to a smooth spacetime bridge or wormhole connecting those regions in the bulk.
Okay, entanglement equals connection.
Right. Then he mathematically reduced the entanglement between those two boundary regions. As the entanglement went down, the area of the minimal surface connecting them got larger and larger. The space-time bridge stretched, thinned, and eventually when the entanglement reached zero, it pinched off completely. The two space-time regions disconnected.
Whoa. So cutting the quantum entanglement literally rips the space apart.
That's the astonishing implication. The connectivity of spacetime, the very fabric holding it together, isn't fundamental. It's a direct consequence, a manifestation of quantum entanglement on the boundary. Spacetime isn't the container, it is the entanglement visualized geometrically.
Okay, this is building towards something huge. I can feel it.
Yeah.
If spacetime geometry emerges from entanglement, where does that lead next?
It leads to perhaps the most audacious conjecture in this whole story. ER equals EPR.
ER equals EPR. Okay, need a translation on that one.
Right. So this was proposed by Leonard Susskind and Juan Moldacena again in 2013. EPR refers to the Einstein-Podolsky-Rosen paradox, basically. Shorthand for quantum entanglement, that spooky action.
Got it.
And ER refers to an Einstein-Rosen bridge, which is the technical term for a wormhole, a theoretical tunnel through spacetime.
So entanglement equals wormholes.
That's the absolutely radical idea. EPR proposes that any two entangled particles, no matter how simple, are connected by a microscopic ER bridge, a tiny wormhole.
Any two, like the two photons we talked about earlier. They have a little wormhole between them.
According to this conjecture, yes, it universalizes the holographic connection between entanglement and geometry right down to the level of individual particle pairs. That spooky connection isn't some ethereal influence. It's a physical, albeit non-traversable, connection through space-time topology.
Non-traversable. So no sci-fi FTL travel through entangled electrons.
Definitely not. We're talking Planck scale structures here, 10 to the minus 35 meters, incredibly tiny, and you can't send anything through them in the classical sense. Causality is preserved. But the implication is staggering.
Which is?
That the smooth, continuous spacetime we perceive is actually an emergent phenomenon built from an unimaginably vast, interconnected network of these microscopic quantum wormholes. Entanglement is the very glue holding space together. Without it, the universe would just dissolve into disconnected points.
Wow, okay. That's a big leap. What's the evidence? Or maybe what problem does this incredible idea help solve?
The most compelling motivation comes from trying to solve perhaps the deepest paradox in black hole physics, the black hole information paradox, and specifically a very sharp version of it called the firewall paradox.
Right, Hawking radiation. Black holes evaporate, but information isn't supposed to be destroyed in quantum mechanics.
Right.
How does that clash?
Okay, so Hawking showed black holes radiate by emitting particles. This radiation arises from entangled pairs created near the horizon. One particle escapes, becoming Hawking radiation. Its partner falls in. Now, for quantum mechanics to be consistent, what we call unitarity, the information about what originally formed the black hole must somehow be encoded in that outgoing radiation. So a late-time radiation particle, let's call it B, must be entangled with the rest of the radiation R that escaped earlier.
Okay, B is entangled with R to get the information out. Makes sense.
But consider an observer freely falling into the black hole. According to general relativity, they should just pass smoothly through the event horizon, no drama. For that to happen, the particle B escaping must also be entangled with its partner particle A that's falling in alongside the observer.
Ah, so B needs to be entangled with R, the outside radiation, and with A, its infalling partner.
Exactly. And here's the killer constraint: monogamy of entanglement. A quantum system, like particle B, cannot be maximally entangled with two other systems, A and R, at the same time. It's quantumly impossible.
Quantum polygamy is forbidden.
Huh, precisely. So in 2012, Amiri, Marolf, Polchinski, and Sully, AMPS, pointed out this sharp conflict. They argued that to preserve information conservation, B entangled with R, the entanglement between the outgoing B and infalling A must break violently. This breakage creates a high-energy curtain, a firewall, right at the event horizon, which would instantly incinerate any infalling observer.
Which completely contradicts GR's smooth horizon. So either information is lost or GR is wrong at the horizon. That's the paradox.
That's the paradox, a major crisis. But EPR offers a stunningly elegant way out.
How? Through the wormholes.
Yes. The conjecture says, what if the infalling particle A is already connected to the distant radiation R via a microscopic ER bridge, a wormhole?
Wait, A inside the black hole is connected to R way outside.
If EPR is true, yes. Because A fell in earlier and R is made of particles that escaped earlier, they share a history traced back to the black hole's formation. They could be part of the same complex entangled state. So if A and R are connected by a wormhole, then B being entangled with A is the same thing as B being entangled with R.
Because A and R are effectively two ends of the same wormhole tunnel.
Exactly. The wormhole bypasses the monogamy conflict. B can be fully entangled with the AR wormhole system. No need to break entanglement at the horizon, no firewall. The infalling observer experiences smooth sailing, GR is happy, and information can still escape.
That is incredibly clever. So the wormholes rescue both GR and quantum mechanics.
They appear to, yes. It suggests something incredibly profound. The topology of space-time, its very connectivity, isn't fixed. It's determined by the quantum entanglement state of matter. What we perceive as distance might just be a classical approximation, hiding these deeper quantum wormhole connections.
This is truly amazing stuff. But, okay, reality check time. It sounds like a lot of this relies on very specific theoretical setups like that ADS space you mentioned. How much of this actually applies to our universe? What are the big hurdles?
You've put your finger on the absolute biggest one. It's often called the cosmological constant problem, but really it's the ADS versus de Sitter problem.
Explain.
Almost all the concrete successes of holography, like AD-SCFT and the detailed EPR arguments, are worked out in anti-de Sitter space. ADS has a negative cosmological constant, negative curvature, and importantly, a nice, static, time-like boundary where the quantum field theory lives. It's mathematically convenient.
But our universe isn't like that.
No. Observations clearly show our universe is expanding at an accelerating rate. This means it has a positive cosmological constant and is best described on large scales by de Sitter DS space. De Sitter space has positive curvature and, crucially, its boundary is in the future, dynamic, and space-like. It's a much trickier beast mathematically.
So the dictionary doesn't work for our actual universe.
We don't have a working dictionary for DS space yet. Extending holography from the mathematically simpler ADS world to the physically relevant DS world is, frankly, the single greatest obstacle facing this entire research program. There's speculative work like DS-DS correspondence or other ideas, but it's very much frontier territory. Applying these beautiful ideas directly to our accelerating cosmos is proving incredibly difficult.
Okay, so that's a major challenge. If this emergent space-time idea coming from string theory and holography has this big hurdle, what's the main alternative view on quantum gravity? You hear about loop quantum gravity. How does that fit in?
That's the other main contender, yes. Loop quantum gravity, or LQG, takes a very different philosophical approach. Instead of saying space-time emerges from something else like quantum fields and entanglement and AD-SCFT, LQG tries to directly quantize Einstein's theory of general relativity itself.
So it applies quantum rules directly to space-time geometry.
Exactly. It takes GR's description of space-time as a dynamical field and applies the standard procedures of quantum mechanics to it. And the startling conclusion it reaches is that space-time itself is fundamentally discrete at the Planck scale. Not emergent, but fundamentally
And
granular.
granular, like made of little bits.
Precisely. In LQG, the smooth fabric of space-time we experience is just a large-scale approximation, like the apparent smoothness of water, which is made of discrete molecules. The fundamental reality is thought to be a network of interconnected loops or edges, a spin network, where quantities like geometric area and volume can only take on specific discrete values. There's a minimum possible area, a minimum volume, an atom of space, if you like.
So it's pixelated space.
That's a good analogy. One of LQG's strengths is that it's inherently background independent. It doesn't assume a pre-existing space-time background to work on. The quantum states are the space-time. It has also had some intriguing results, like potentially resolving the Big Bang singularity into a big bounce, where the universe contracted and then bounced back out.
But it has its own challenges, too.
Oh, absolutely. A major one is consistently showing how the smooth space-time of classical general relativity emerges from this discrete structure at low energies. That's called the semi-classical limit, and it's tough. Incorporating matter, the particles of the standard model, is also challenging, as is fully resolving some conceptual issues like the problem of time in quantum gravity.
So maybe we can quickly compare them. Emergent spacetime versus loop quantum gravity.
Sure. Fundamentally, emergent spacetime, via add SCFT, ER-EPR, sees quantum fields and entanglement as primary, with spacetime geometry emerging. LQG sees spacetime geometry itself as fundamental, but quantized, made of discrete units.
Nature of spacetime.
Emergent says continuous, but arising from non-spatiotemporal stuff. LQG says fundamentally discrete.
Role of entanglement.
For emergent, it's the glue that builds space. For LQG, it's more a property of matter living on the quantum spacetime.
Background dependence.
ADA-CFT is generally background dependent. It assumes the ADA-S background. LQG is background independent.
Key successes.
ADA-CFT dictionary, insights into black hole paradoxes for emergent, quantization of airy volume, big bounce cosmology for LQG,
Major challenges.
applying holography to our De Sitter universe, proving conjectures for emergent, recovering classical GR, incorporating matter for LQG. They're quite different paradigms.
Definitely different flavors.
Yeah.
Which brings up a huge question for both, really. These ideas operate at the Planck scale, ridiculously tiny energy scales. How can we possibly test any of this? Is it even science if it's not falsifiable?
That is a very serious criticism, particularly leveled against the emergent spacetime program derived from string theory. There's a distinct lack of direct, testable, experimental predictions right now. The Planck scale itself, 1035 meters, is just unimaginably far beyond anything we can probe directly with particle accelerators.
And those microscopic wormholes from EPR, no way to see those?
Not directly, no. They're far too small and non-traversable. Plus, many of these models rely on assumptions that are themselves unproven, like the full validity of the ADA-CFT correspondence beyond specific examples, or the existence of things like supersymmetry, which we haven't seen any evidence for experimentally.
So, is it hopeless? Or are there indirect ways to look for hints?
There are definitely indirect avenues people are pursuing, though they are long shots. One exciting area is analog gravity systems.
Analog gravity, like building a black hole in the lab.
Sort of. Not a real black hole, but using other physical systems like ultra-cold atoms, fluids, or superconducting circuits that can be engineered, so their collective behavior is described by equations similar to those of gravity and curved spacetime. If you can create highly entangled states in these systems, you might see geometric properties emerge in ways predicted by holography, or maybe even mimic wormhole dynamics.
So test the principle, even if not quantum gravity itself.
Exactly. Validate the core concept that geometry can emerge from entanglement. Another route is through cosmological and astrophysical probes. Looking for extremely subtle imprints of quantum gravity from the very early universe in the cosmic microwave background radiation, or perhaps in the distribution of galaxies, or even in signals from gravitational waves.
Tiny deviations from standard predictions.
Tiny deviations, or perhaps unexpected correlations. And related to that is quantum gravity phenomenology, which specifically looks for violations of known physical laws that might be caused by quantum gravity effects. A classic example is searching for tiny variations in the speed of light for photons of different energies, which could happen if space-time isn't perfectly smooth but has some kind of granular structure, potentially violating Lorentz invariance.
So searching for cracks in the foundations of current physics.
Pretty much. It's tough. The expected effects are incredibly small, but it's the best hope we have right now for some kind of experimental or observational handle on these ideas. Stepping back, though, if this idea that spacetime is emergent turns out to be right, the implications go way beyond just physics equations. They force us to rethink our whole picture of reality.
How so?
Well, first, there's this idea of the illusion of locality, our fundamental intuition of here and there, of distinct places separated by distance. That might just be a macroscopic approximation, a trick of scale. The deeper reality could be this fundamentally non-local quantum network where, in some sense, everything is connected.
Distance isn't real. That's a tough one to swallow.
It is, and it gets even weirder when you think about time.
Oh boy. Time isn't real either.
Well, it might also be emergent. There have been hints of this for a long time. Some formalisms in quantum gravity, like the Wheeler-DeWitt equation, famously don't even have a time variable in them. They describe a seemingly static, timeless quantum state for the entire universe.
A frozen universe. How can that be when we clearly experience time flowing?
The emergent spacetime idea offers a potential answer. Perhaps the fundamental quantum state of the universe is static, but time emerges for observers within the system. An observer, being part of the universe, is entangled with it. This entanglement, this correlation, could be what creates the perception of change and flow of time passing. There have even been some toy model experiments.
Experiment?
Yeah, by Moreva and colleagues, using entangled photons. They showed that from an external perspective, their little quantum system looks static, timeless. But an internal observer, represented by correlations within the system, would perceive evolution, a clock ticking. It suggests time could be relational, subjective, emergent from entanglement.
So space, time, locality. What about cause and effect, determinism?
Those could also be emergent properties. The fundamental laws might be deterministic in some hidden way, but the randomness and causality we see could be statistical features that emerge at a macroscopic scale, much like temperature emerges from the chaotic motion of molecules.
And does the observer consciousness play any role in this? You sometimes hear really out there ideas.
Well, most physicists try to avoid going too far down that path, but some interpretations do brush up against it. The idea that space-time itself might emerge or crystallize through the act of observation by entangled, conscious observers, that's sometimes called the participatory anthropic principle. It's highly speculative, bordering on philosophy, but it shows how deep these questions go.
Okay, so given all these mind-bending possibilities and the huge challenges, where does the research go from here? What are people focusing on?
Well, as we discussed, extending holography to realistic cosmologies, figuring out how it works in de Sitter space, that remains arguably the most critical theoretical task. If that nut can be cracked, it would be revolutionary.
Right, making it relevant to us.
Exactly. Another really active area is exploring the connections between entanglement, complexity, and spacetime. There's another related conjecture, sometimes called complexity equals volume, which suggests that the volume of a wormhole connecting two boundary regions grows over time in proportion to the increasing computational complexity of the quantum state on the boundary.
Computational complexity, like how hard it is to simulate the state on a quantum computer.
Essentially, yes. It's another potential entry in that holographic dictionary, linking geometry not just to entanglement, but to computation itself. It hints at deep connections between gravity, quantum mechanics, and information processing.
Which words too?
To the growing realization that quantum information science is becoming a guiding principle. Physicists are increasingly using concepts from quantum computing, like entanglement measures, quantum error correction codes, which surprisingly resemble aspects of ADA CFT, and complexity theory as tools to try and decode spacetime. The hope is that by understanding the structure of quantum information, we might be able to sort of reverse engineer the code from which spacetime geometry emerges. It's a really exciting fusion of fields. So when you really step back, this whole quest for quantum gravity, especially through the lens of emergent spacetime, it morphs into something even deeper. It becomes a search for a new fundamental ontology, a new understanding of what reality is at its most basic level.
It's not just physics anymore.
Not at all. It's forcing physics, computer science, information theory, and even philosophy to converge in really fascinating ways. The answer to the question, what is spacetime, might turn out to be completely inseparable from the question, what is information? It leaves us with this provocative thought. The universe we see, the one we inhabit with its incredible vastness, its seemingly relentless flow of time, its solid sense of place. All of it might just be a grand illusion. a kind of hologram projected from a deeper reality that's timeless, non-local, and fundamentally woven from quantum information.
Okay, my brain officially hurts, but in a good way. We've gone from Einstein's elegant curves to quantum spookiness, through holographic projections and universe-spanning wormholes, and questioned the very reality of space and time. What a journey. It really makes you wonder, doesn't it? How does hearing about this potentially shift your own perception of reality, of just being here?
And what new questions does this raise for you? When you start thinking about the universe as potentially being built from bits of information connected by entanglement, what does that spark?
Absolutely fascinating stuff to ponder. Thank you for joining us on this incredibly deep dive into the very fabric of reality. As always, stay curious.